We're never going to stop exploring the unknown in air and space.
Voyager, in some very real sense, is material that's not from the medium in which it finds it.
Something we never anticipated was discovered on Voyager 2's voyage to the solar system's boundary, and it's not good news. The probe discovered a chaotic red sea of charged particles and a deteriorating heliosphere as it entered interstellar space. These discoveries cast doubt on Earth's defenses against cosmic radiation and the threats that lie outside our solar system. What does this portend for the future of earthly life and perhaps interstellar travel? Let's examine the disturbing specifics. As we examine the startling findings near the solar system's edge, stay tuned. Deep Space Exploration's Foundations. Exploration of deep space did not happen immediately. It was founded on decades of advancements in science and technology, as well as people's insatiable curiosity in the cosmos. A combination of early space missions, competition during the Cold War, and groundbreaking discoveries that pushed the boundaries of what was feasible created the groundwork for exploring beyond Earth's orbit. The space race between the US and the USSR in the 1950s and 1960s marked the start of the adventure, as both countries sought to prove their dominance in science and technology. The Soviet Union's successful 1957 launch of Sputnik, the first satellite to orbit the Earth, was a significant event. The world was stunned, and the US was compelled to step up its space ambitions. As a result, NASA was created in 1958, marking the start of the space exploration era. Near-Earth targets were the focus of early milestones. In 1958, the United States launched its first successful satellite, Explorer 1, which found the Van Allen radiation belts that round the planet. Subsequently, the Soviet Union achieved even more ambitious feats, including the 1961 launch of Yuri Gagarin, the first human, into space. President John F. Kennedy's audacious claim that the United States will send a man to the moon resulted from this. This objective was accomplished in 1969 with famous Apollo 11 mission. Although scientists' immediate attention was on the moon, they were already considering more ambitious ideas. NASA's Mariner program and other missions cleared the path for interplanetary travel. Launched in 1962, Mariner 2 was the first spacecraft to successfully fly past Venus, exposing it as a hostile, sweltering planet. The first close-up photos of Mars were returned by Mariner 4 in 1965, forever altering our perception of the red planet. Important developments in spacecraft design included the utilization of gravity assist maneuvers and the creation of radioisotope thermoelectric generators, RTGS, for power. These technologies paved the way for humanity's most ambitious adventures by enabling programs like the Voyager program to go into the outer solar system. These early endeavors set the foundation for what we currently know about deep space, from Cold War rivalry to groundbreaking discoveries, the space race, and the beginnings of the Cold War. The Cold War, a time of fierce geopolitical competition between the US and the USSR, is closely linked to the beginnings of deep space exploration. Military might wasn't the only factor in this contest. It spread into science and technology, resulting in the space race, a significant historical period that prepared the way for humankind's exploration of the universe. When the Soviet Union shocked the world by launching Sputnik 1, the first artificial satellite, in 1957, the space race officially began. This little beeping device in Earth's orbit was more than simply a piece of technology. It represented the might and scientific superiority of the Soviet Union. It served as a wake-up call for the US. The US government acted swiftly because of concern that it might lag behind in space technology, especially in its military applications. To manage American space exploration endeavors, the National Aeronautics and Space Administration, NASA, was established in 1958. The Soviet Union dominated early space race accomplishments. Laika, the first living thing, was launched into space on Sputnik 2 after Sputnik. Then, in 1961, Soviet cosmonaut Yuri Gagarin traveled in Vostok 1 to become the first person to orbit the Earth. In addition to being scientific triumphs, These turning points dealt serious blows to American reputation and pride. The United States reacted with audacious aim. In a landmark 1961 speech, President John F. Kennedy famously stated that the objective was to put a man on the moon by the end of the decade. The Apollo program and the momentous Apollo 11 mission, which saw Neil Armstrong and Buzz Aldrin become the first people to step foot on the moon in 1969, were made possible by this. It solidified America's dominance in space exploration and was a turning point in the space race. The space race developed technology for deeper exploration, but the moon was the main focus. Rocket technology, satellite communications, and spacecraft design advanced quickly as a result of the Cold War rivalry. And these advancements would later assist missions like as Voyager and Mariner. These competitive successes served as the cornerstone for humanity's expedition into the vast, uncharted territory of deep space, important early U.S. space operations. Pushing boundaries and demonstrating that humanity could travel beyond Earth were the main goals of U.S. space research in its early years. Future space travel, including trips to the Moon, Mars, and perhaps interstellar space, was made possible in large part by these missions. Every mission served as a springboard, expanding scientific knowledge, technology, and the country's capacity to explore farther into space. The 1958 launch of Explorer 1 was one of the earliest significant turning points. This signified the United States' entry into the space race and was the country's first successful satellite. The objective of Explorer 1 was not merely symbolic. The Van Allen radiation belts, a significant advancement in our knowledge of Earth's magnetic environment, were discovered because of the scientific instruments it carried. This accomplishment paved the way for more ambitious missions by demonstrating that space exploration could produce useful scientific data. The first manned spaceflight program in the United States was called Mercury, and it started in 1959. Sending a human into space and safely returning them to Earth was its straightforward but difficult mission. During the brief 15-minute suborbital flight of Freedom 7, astronaut Alan Shepard became the first American in space in 1961. More sophisticated missions were made possible by the Mercury program's success, which demonstrated that people could live and work in space. The Gemini program followed, concentrating on creating the technology and expertise required for lunar exploration. Spacewalks, orbital docking, and long-duration flights, all crucial for the future Apollo program, were tested during the 1965 to 1966 Gemini missions. Gemini astronauts demonstrated that humans could survive prolonged space travel by spending up to 2 weeks in orbit. The Apollo program, whose pinnacle accomplishment was the Apollo 11 moon landing in 1969, was the result of these early missions. The Apollo program showed off humanity's capacity to explore places beyond Earth in addition to its technological capabilities. Future space exploration, from robotic probes to interstellar missions like Voyager, was made possible by these pioneering expeditions. Innovation in technology. Humanity's ability to travel into space and explore the unknown has been fueled by technological advancements. In order to overcome obstacles like great distances, finite power supplies, and accurate navigation, deep space travel in particular demanded creative solutions. These discoveries expanded our understanding of what was possible in space and enabled missions like Voyager. The creation of the gravity assist maneuver, commonly referred to as the slingshot technique, was one of the most important developments. This groundbreaking technique accelerates spaceships without the need for more fuel by harnessing the gravitational pull of planets. Gravity assist, which was first effectively used in the Mariner 10 mission to Mercury in 1973, became a key component of missions such as Voyager, enabling spacecraft to visit several planets in a single mission. This method allowed Voyager to make a grand tour of the outer planets, launching past Jupiter and Saturn to reach Neptune, Uranus, and ultimately interstellar space. The development of radioisotope thermoelectric generators, or RTGs, was another significant advance. RTGs use the natural decay of radioactive isotopes like plutonium-238 to produce electricity, in contrast to solar panels, which are useless in the faint light of the outer solar system. Long-duration missions like Voyager were made feasible by this dependable power supply, which guaranteed that the spacecraft could transmit data for decades after launch, even in the icy, dark depths of interstellar space. Another problem was communication over long distances. Even from billions of miles away, spacecraft like Voyager were able to transmit data back to Earth because to NASA's Deep Space Network, DSN, a global system of enormous radio antennae. Given that it now takes more than 22 hours for signals from Voyager 1 to reach Earth at the speed of light, the DSN had to be extremely sensitive. Humanity was able to explore the far reaches of the solar system and beyond because to technical advancements like gravity assist, RTGS, and the DSN. They continue to influence the direction of space exploration and stand as a testimony to human ingenuity. Creation and launch of the Voyager program. Exploring the outer planets and venturing into unexplored areas of interstellar space was the original goal of the Voyager program. A once-in-a-lifetime 176-year planetary alignment gave spacecraft the potential to use gravity assistance to visit many planets on a single trip, which led to the program's 1977 launch. The Voyager program was one of NASA's most ambitious endeavors because of this alignment, technological developments, and a growing interest in the outer solar system. Originally, the Grand Tour, a more comprehensive plan that sought to investigate Jupiter, Saturn, Uranus, and Neptune, included the concept for the Voyager missions. NASA's Jet Propulsion Laboratory, or JPL, improved the mission's design and goals as it developed in the early 1970s, ultimately producing Voyager 1 and Voyager 2, two identical spacecraft, to gather comprehensive information about the planets, their moons, and magnetic fields. Each was outfitted with cutting-edge scientific equipment. On August 20th, 1977, Voyager 2 was launched, and on September 5th, 1977, Voyager 1 was launched. Voyager 1 reached Jupiter and Saturn before Voyager 2 because it was put on a quicker trajectory despite being launched second. In order to visit several worlds without using more fuel, both spacecraft relied on the revolutionary gravity assist maneuver, which harnessed each planet's gravitational pull to accelerate and reroute their routes. Along with its scientific goals, the Golden Record, a photograph that included sounds, music, and pictures of Earth, was taken on both missions as a warning to any alien life that might come into contact with the spaceship. The Voyager program's launch signaled the start of an endeavor that revolutionized space travel. The trip to the outer planets wasn't the only thing involved. Humanity's first step toward interplanetary exploration was this, a mission that still informs and inspires people today. First, Voyager. One of humanity's greatest accomplishments is Voyager 1. More space than any previous man-made object has traveled from Earth. Just 16 days after its twin, Voyager 2, it was launched on September 5th, 1977, with the goal of exploring the outer planets before continuing on into interstellar space. Voyager 1 has revolutionized our knowledge of the solar system and beyond throughout the decades by providing groundbreaking data. Studying Jupiter, Saturn, their moons, and their environs was the mission's original objective. When Voyager 1 returned detailed photographs of Jupiter's Great Red Spot and found active volcanoes on the moon Io, the first indication of active volcanism outside of Earth, it made history. Voyager 1 examined Titan, Saturn's largest moon, whose dense atmosphere suggested conditions akin to those of early Earth, and unveiled detailed information on the planet's ring. Just these discoveries were enormous. However, the mission of Voyager 1 was far from finished. Voyager 1 was put on a course that would lead it out of the solar system following its 1980 flyby of Saturn. Decades later, on August 25, 2012, it crossed the heliosphere, the line where the sun's influence ends, to become the first man-made object to enter interstellar space. As Voyager 1 started sending data from the interstellar medium, a zone full of charged particles and cosmic rays, powered by radioisotope thermoelectric generators, or RTGs, this was a momentous milestone. Despite being more than 14.8 billion miles away from Earth, Voyager 1 is still returning data. To save energy, its instruments are gradually shutting down. However, its heritage is safe since it conveys a message to possible extraterrestrial civilizations through the Golden Record. Humanity's emissary to the universe, Voyager 1, is evidence of our inventiveness and curiosity. Voyager 2. Launched on August 20th, 1977, Voyager 2 is one of the most ambitious and revolutionary space exploration missions ever. This spacecraft, which was a part of NASA's renowned Voyager program, was built to investigate the outer planets and advance human knowledge of the solar system. Voyager 2 has accomplished a number of incredible firsts throughout the years, offering priceless information about some of the most enigmatic and far-off worlds in our cosmic neighborhood. The course of Voyager 2 led to an unparalleled grand tour of the outer planets. It made a close flyby of Jupiter in 1979 and took breathtaking pictures of its moon, enormous storms, and tumultuous atmosphere. It sparked conjecture about underground oceans by finding icy surfaces on Europa and active volcanoes on Io, the first indication of volcanic activity outside of Earth. When Voyager 2 arrived at Saturn in 1981, it investigated the planet's complex ring system and its moons, including Enceladus, which was later discovered to feature water vapor geysers. Then, in 1986, Voyager 2 became the first and only spacecraft to visit Uranus. 10 new moons were found, along with a featureless blue-green planet with a tilted magnetic field. In 1989, as Voyager 2 continued its mission, it passed Neptune and took the first close-up pictures of the planet's big dark area, a huge storm, and its deep blue atmosphere. Additionally, it investigated Triton, the moon of Neptune, and discovered evidence of liquid nitrogen gushing from geysers. Voyager 2 completed its planetary visit and proceeded on its outbound journey. It became the second spacecraft to leave the heliosphere, the Sun's protective bubble, when it entered interstellar space in 2018. Voyager 2 is still in operation and is returning useful information on the interstellar medium. Voyager is a monument to human ingenuity and our desire to comprehend the universe. Americans want the U.S. to continue to lead the world in space exploration. Radio-based power systems are essential. One of the main obstacles NASA had when designing the Voyager spacecraft was determining how to power them. Because sunlight in the outer solar system is too feeble to provide adequate energy, the Voyagers were unable to rely on solar panels like missions closer to the sun could. Instead, NASA used radioisotope thermoelectric generators, or RTGs, a groundbreaking power source. While traveling billions of kilometers from Earth, these devices supplied the consistent, long-lasting energy required to keep Voyager systems operating. RTGs generate power by harnessing the heat generated by the natural decay of radioactive elements, particularly plutonium-238. The slow decay of plutonium-238 releases heat, which the rubles then use to generate electricity. Because there are no moving parts in this process, RTGs are extremely durable and perfect for the harsh conditions found in deep space. At launch, the 3 RTGs that were installed on each Voyager generated roughly 470 W of electricity. The RTGs were built to last for decades, well beyond the spacecraft's initial mission timetable, even though the power production gradually drops as the plutonium decays. Critical systems like onboard computers, communication networks, and research instruments depend on this power system to function. Voyager 1 and Voyager 2 are still sending data back to Earth almost 45 years after launch. To save energy for the most crucial task, NASA has had to gradually turn down non-essential equipment when their power supply runs low. Space exploration expeditions to far-off, Dark parts of the solar system and beyond have been made possible by RTGs. They were essential to the Voyager's amazing voyage past Jupiter, Saturn, Uranus, Neptune, and now into interstellar space. The Voyager's accomplishment emphasizes how crucial creative power solutions are for upcoming deep space missions. Communications through the network in outer space. It's no easy task to communicate with spacecraft like Voyager 1 and Voyager 2, which are billions of miles away. NASA uses the Deep Space Network DSN, a global network of massive radio antennas intended to track and connect with spacecraft orbiting far from Earth to do this. One of the most important parts of deep space research is the DSN, which makes sure that information gathered by probes like the Voyagers can be sent back to Earth. The DSN is made up of 3 ground facilities in California, USA, Madrid, Spain, and Canberra, Australia, which are positioned about 120 degrees apart. As Earth spins, this configuration guarantees constant contact with spacecraft. Massive radio antennae, the largest of which is 70 meters, 230 feet in diameter, are installed in each site. These antennas are made to pick up even the smallest signals from spacecraft that are billions of kilometers away. For example, it takes more than 22 hours for signals from Voyager 1, which is currently more than 14 billion miles away from Earth, to reach us. These signals are billions of times less than the power of a typical light bulb by the time they reach their destination. Because of their extraordinary sensitivity, the DSN's antennas can pick up these faint signals, amplify them, and decode the information they contain. Additionally, the DSN is essential for communicating commands to spacecraft. Voyager's instruments, trajectory, and declining power supply can all be controlled remotely by engineers. For the spacecraft to effectively complete its mission, this two-way communication is necessary. The DSN continues to be Voyager's lifeline to Earth as it travels farther into interstellar space. We would never have access to the groundbreaking information uncovered by the Voyager missions and other far space probes without this incredible network, leaving many mysteries of the universe unsolved, finding that the heliosphere is getting smaller. The discovery of a diminishing heliosphere was one of the most unexpected results of Voyager 2's voyage into interstellar space. The Sun's solar wind forms the heliosphere, a huge bubble-like zone that stretches well beyond the planets and serves as a shield against dangerous cosmic rays from interstellar space. For a long time, scientists thought it was a strong, all-encompassing shield. However, the data from Voyager 2 showed a different picture, one that poses important queries regarding the prospects for both life on Earth and interplanetary travel. 2018 saw Voyager 2 crossed the heliosphere, the line separating interstellar space from the Sun's influence. Voyager 2 was only the second man-made object to leave the heliosphere, making it a historic event, but the heliosphere was weaker and smaller than previously believed, according to the spacecraft's instrumentation. The heliosphere seems to have diminished, leaving the solar system more susceptible to cosmic radiation, rather than a strong barrier that stretches far into space. There may be significant repercussions from this heliosphere shrinkage. Earth and other planets are protected from harmful high-energy particles that come from beyond the solar system by the heliosphere. More of these cosmic rays could go farther into the solar system if the heliosphere weakens, which could have an impact on satellites, upcoming space missions, and even Earth itself. Although Earth's atmosphere offers a robust defense against cosmic rays, an increase in radiation could nevertheless have an effect on biological processes, technology, and climatic systems. Extended exposure to elevated cosmic ray levels may provide difficulties for deep space travelers or possibly have an impact on satellite electronics while in orbit. The finding of a decreasing heliosphere by Voyager 2 emphasizes how closely the solar system and the Sun's activity are related. It serves as a reminder of how little we actually know about how dynamic space is, how it affects our planet, and how it will affect future exploration. Red Sea of turbulent plasma near the frontier of the solar system. In 2018, Voyager 2 entered an unexplored area of space as it crossed the heliosphere, revealing a dynamic and chaotic environment that scientists have dubbed a turbulent plasma Red Sea. The solar wind, a torrent of charged particles from the sun, collides with the interstellar medium in this region near the boundary of the solar system to form a whirling, erratic ocean of plasma. Our knowledge of the boundary between solar systems and the forces operating in interstellar space has been drastically altered by the data gathered by Voyager 2. The heliosphere is the line separating interstellar space from the heliosphere, the protective bubble formed by the sun's solar wind. The termination shock, a tumultuous region where the solar wind drastically slows and starts to mingle with interstellar particles, was encountered by Voyager 2 as it crossed into this barrier. This transition area is anything but smooth, as seen by the hotter, denser, and more turbulent plasma observed by Voyager 2's instruments. The satellite saw a complex structure of plasma currents, chaotic fluxes of charged particles, and abrupt changes in the magnetic field. Older models that projected a quiet and steady transition into interstellar space are challenged by this turbulence, which is compared to a stormy ocean. Rather, Voyager 2 discovered a dramatic interplay between the enormous forces of the interstellar medium and the influence of the sun. This discovery has significant ramifications. It draws attention to the difficulties that future spacecraft may have when moving outside of the solar system to start. Instruments and onboard equipment may be seriously at risk from the severe turbulence and high-energy particles in this area. This discovery also clarifies the function of the heliosphere as a shield, which has been eroding and becoming less effective, allowing more cosmic radiation to enter the solar system. The discovery of this plasma Red Sea by Voyager 2 highlights how erratic and volatile the boundary of the solar system is. It serves as a sobering reminder of how little is understood about how the sun and the galaxy beyond interact. Furthermore, it poses significant queries for interstellar travel in the future. Ramifications and cautions for upcoming space travel. Ramifications and cautions for upcoming space travel. The Voyager spacecraft's findings have significant ramifications for space exploration going forward. The knowledge gained from Voyager highlights the difficulties and dangers that await us as we prepare trips to the outer planets and beyond. The results demonstrate that space is more dynamic, unpredictable, and hazardous than previously thought, from the heliosphere shrinkage to the turbulent plasma regions at the boundary of the solar system. The sun's solar wind creates a protective bubble called the heliosphere, which is diminishing. This is one of the most important warnings. The heliosphere is weaker and smaller than anticipated, according to data from Voyager 2, which exposes the solar system to more cosmic radiation from interstellar space. The radiation dangers for both robotic and crewed missions venturing outside of Earth's atmosphere may rise as a result of this deteriorating barrier. Long-term exposure to high-energy cosmic rays could be extremely harmful to people on deep space missions, and spacecraft systems could malfunction or sustain damage. To withstand these increasingly severe conditions, future missions will need to create more resilient technology and sophisticated radiation shielding. Another level of intricacy is introduced by the turbulent plasma zone, which is frequently referred to as a Red Sea. Far more violent than previously believed, this chaotic zone is found where the solar wind meets the interstellar medium. This region was hot, thick, and teeming with erratic changes in plasma flows and magnetic fields, according to Voyager 2. In order to assure safe transit in such zones, spacecraft must be outfitted with instruments that can survive harsh circumstances and measure the environment precisely. The long-term effects of a diminishing heliosphere on Earth itself are arguably the most urgent issue. Even while our atmosphere provides a great deal of protection from cosmic radiation, biological processes, climatic systems, and contemporary technology like power grids and satellites might all be impacted by an inflow of high-energy particles. The necessity of ongoing heliosphere and border monitoring is underscored by the interdependence of Earth systems with solar activity. The findings of Voyager highlight the necessity of cutting-edge planning and inventive technologies for further exploration. The issues Voyager uncovered will influence the design of missions that want to explore planets, moons, and beyond, from better propulsion systems to better radiation protection. These results are more than a warning. They serve as a wake-up call telling us that venturing into the unknown necessitates readiness, fortitude, and creativity. Thank you for watching the video. Please like and subscribe for similar content.